Welcome to practice number 6 of CircuitLab. This is going to cover electric charge, fields, and capacitors. My name is Mr. Burleson, and you can reach me at geaux15@hotmail.com. So we're going to go over our normal agenda today. So what is an electric charge? An electric charge is a physical property of matter that causes it to experience a force when placed in an electromagnetic field. In other words, a charge is impacted by a field, but it also creates a field. There are two types of electric charges, both positive and negative, commonly carried by protons, being positive, and electrons, respectively. Just like when we talked about magnetism, like charges repel each other and opposites attract. Now, the unit that we're going to use for charge is called coulombs, and it is always conserved. In other words, you can neither create nor destroy charges. An electron has a charge of 1.602 times 10 to the negative 19 coulombs. So that is a period with 18 zeros, then 1602. So very, very small number of coulombs. So when we draw electric field lines, as we do here on the right, you'll notice that we draw a positive and a negative, and the electric field lines always radiate out of the positive, like in the lower left here, like a sun, okay? And then they are attracted, the electric field lines are attracted and pulled into a negative field charge, like in the lower right hand. Think of it like a black hole. And so what you'll notice here is that the electric field lines on the opposite sides of the positive and negative are really not impacted too much. They go out forever, okay? However, in between, they're bent and they're brought in. And so this is very important because you'll probably ask this on at least one or two tests to draw the electric field line. So what is Coulombs Law? Well, it determines the force of attraction or repulsion between two charges. So what you do is you determine the force first, and then you look, and if they're alike, they're repulsed. And if you look in their opposite, they'll be attracted. Okay? The force will be in newtons. K is Coulomb's constant, equal to about 8.99 or 9 times 10 to the 9th Newton meter squared divided by Coulomb squared. Okay? Q1 and Q2 are the charges in coulombs. So keep in mind, we could have something where we have like a block of protons that could have a sizable number of positive charges, and we could have a block of electrons that have a sizable number of negative charges. Okay? R is the distance in meters between the centers of charges, and you notice it's divided by r squared. So that if this looks, you're thinking, wow, this looks a lot like Newton's gravitational field equation, you'd be absolutely right. Now, remember, groups of charges can be combined into an equivalent charge. And also keep in mind, a lot of times our charged particles are going to be ions, and so these are atoms that either have extra electrons, more electrons than they have protons, or they have fewer electrons, and they form a charge. And again, down below, this little picture here sort of describes everything. So what you see here is that in the lower right hand corner, you'll notice that the like positive charges are pushed away from each other and the opposite positive and negative charges are attracted, but yet the force equation is actually the same, and the force is the same. It's just whether or not it is attracted or repulsed. Now, you'll notice in the middle right hand side we have a system where we have a series of positive and negative charges. And what I just realized when I looked at this is that this is an error. Okay, you'll notice off to the right that this actually is more, it's loops, so therefore it must be magnetic. So that one is going to be one we're going to have to fix. So what is a capacitor? A capacitor is a passive two-terminal electrical component that stores potential energy in an electric field. So in other words, it puts positive charges on one side, negative charges on the other, and that electric field forms, sort of saves the energy. Okay. Now, they will usually have two electrical conductors, and they will be separated by some form of dielectric medium. So in other words, it's going to be some sort of non-conductive medium like glass, ceramic, plastic, paper, mica, etc. Okay, now keep in mind the conductor can be foil, thin film, some type of metal, electric light, and the unit that they use to talk about capacitance is farad, after Michael Faraday. Okay, now keep in mind most capacitors that you'll see, and you'll see like some pictures in the lower right hand corner, these are what capacitors look like. They're going to have really small values like microfarads, picofarads, nanofarads. Okay, up above is how we would draw a capacitor in a diagram. Okay, and so what you'll notice, like a normal fixed capacitor, it's just two parallel plates because that's how they initially started building them. And then you'll notice one that's got a straight line and a curved line, and the straight line would be the side that's always going to be positive. So it's designed such that the positive charges would be on top. And then if you draw a line through the plates, that shows that it's a variable capacitor. And this was very common, especially when you had to tune a radio. Okay, and we had to change the constant. The one thing I want you to remember, and one of the equations that you really need to write down in addition to Coulombs Law before, is Q equals CV. Okay, so in other words, the total charge is equal to the capacitance times the voltage. Okay, sometimes you're going to be asked to solve for the voltage, sometimes you're going to be asked to solve for the capacitance, sometimes you're going to be asked to solve for the charge. So here is how you would normally draw a capacitor. Okay, so you'll notice that on one side of if we look in the middle diagram onto the right, you'll notice we have all the positive charges on the left hand side, we have all the negative charges on the right hand side. So you'll notice that we have a very uniform electric field in there, and that electric field, since the charges can't move from one side to the other, okay, in a steady state, it saves all that energy. Okay, so when charging to the current flows freely at first, it appears to be a short. So in other words, when you first charge up a capacitor, it's going to look like a short. But then as the charges start together, it's going to slowly stop the flowing of electrons, and it's going to be an open. Okay, so, and it's going to have its maximum voltage. So to give you an idea, a capacitance of 1 farad means that 1 coulomb of charge on each conductor causes a voltage of 1 volt. Okay, now you'll also notice here is that the capacitance will be determined by the size of the area and the distance d, and what type of dielectric you're going to put into the middle there. Okay, so that is, and by the way, that d is going to be really small. Okay, so the thing I want you to also remember is that we have another equation for calculating the capacitance. Okay, and that is the capacitance is equal to epsilon, okay, which is the dielectric permittivity of the material, and that determines how much capacitance can be held, times the area divided by the d. So the smaller the d, the bigger the capacitance. The bigger the A, the bigger the capacitance. So if you want a high capacitance capacitor, it will have a very large area and a very small d. Okay, now the energy, that's another equation to keep in mind. Okay, now the other thing is that the energy stored in the capacitor is equal to 1/2 CV squared. Okay, and if it looks a little bit like kinetic energy, you would not be wrong in noticing that it's very similar. So, one other thing to keep in mind: D is normally much smaller. You're talking like on the order of sub-millimeters or millimeters. whereas A is going to be much, much larger. So you're talking like orders of magnitude difference. The area is always much bigger than the D. Now, keep in mind that the free space or vacuum has a permittivity of 8.854 times 10 to the minus 12 farads divided by meters. Okay? All other materials will be higher. Okay? Some materials are twice that much, some materials are 100 times that much. Some materials are even much greater times that much. But free space is that number. Now, keep in mind also that air is very, very close to that. And yes, there are air capacitors. So, what I'd like you to do in your in-practice quiz is talk about what are conducting materials, what are insulating materials, what are semiconducting materials, and think about the examples, okay? Go back to use your homework generator in your binder. Remember, you can always use your binder in these in-practice quizzes, and I want you to be able to find those. And then in the diagram below here, I want you to draw the electric field lines. Okay, we're also going to do this type of divider problem. Okay, you'll notice that this is from a previous quiz, and I want you to really be able to quickly be able to determine the voltage drop across each resistor. I want you to notice whether the current or the voltage is split, and then use the appropriate method. So let's talk about this one as well. In practice, if two electrons are 1 millimeter apart, are they attracted or repulsed? What is the force between them? And draw the electric field diagram, but not the scale. In other words, I want you to draw two electrons. I want you to label whether they're positive, negative charges, and I want you to tell me if they are attracted or repulsed. And then I want you to use that equation. Remember, we had 4 equations that we covered today, and I want you to draw the force between them. Now, if two protons are 1 millimeter apart, I want you to do the same 3 questions. And then if an electron and a proton are 1 millimeter apart, are they attracted or repulsed? What's the force between them? And draw the electric field diagram, not to scale. So these 3 cases are going to be very, very similar. And in fact, I'll even give you a hint. The force is going to be the same in absolutely each one of these cases. The force will be the same. The difference is whether they're attracted or repulsed. Okay? And so really do your level best to answer those questions. For homework, what I'd like you to do is know what common materials are used to charge. In other words, silk cloth, glass, etc. You'll remember there's a very famous experiment that Ben Franklin did with silk cloth and a glass rod. I also want you to explain how a balloon that is rubbed on someone's head sticks to the ceiling. You'll notice we're talking about static charges here. What are the common ways to prevent static charge or discharge? And I want you to draw the electric field lines for positive, negative, and mixed charges. So there's 4 different ways you can draw this up. 2 positives, 2 negatives, positive and a negative and a positive. Determine the force between a 10 coulomb and a minus 100 coulomb set of charges that are 1 meter apart, and figure out whether or not they're repulsed or attracted. Thank you so much. That is practice number 6.